Hello, my name is Brandon, and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome, it's great to have you. If you are a returning viewer, it is great to have you back. If you like this video, please give it a thumbs up, share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. Now that we are introduced, let's go ahead and get started. In this video, we will take an in-depth look at forward selection, which is one of 4 common multiple regression techniques. Now, forward selection on the surface is easy to understand, but what we're going to do is go under the hood and look at the actual numbers so we understand how our models are actually put together. It's not good enough to go into a software program, click a few buttons and get a model out and have no idea what's going on. So we will go over the basics and then dive into the actual numbers so you understand fundamentally what is going on. Let's get to it. So there are 3 common techniques for building iterative regression models: forward selection, backward elimination, and stepwise regression. You've probably heard of these before. The 4th common technique is not iterative. It is called best subsets regression. Now, best subsets examines all possible combinations of feature variables. It is a brute force method that can be computationally expensive. For example, let's say you have a relatively small model and you have 9 feature variables. Well, for each model that has 2 variables in it, there are 36 possibilities. For each model that has 3 variables in it, there are 84 possibilities. And best subsets will examine all of them, all the way up to all 9 variables. That's hundreds of models. Now, luckily, the analyst can specify the maximum number of features. Let's say you want to limit it to 5 feature variables. Well, it can stop there. The analyst can also request the best 2 or 3 models for each number of feature variables. So you can say, hey, I want the 3 best models that are single variable, the 3 best models that are 2 variable, the 3 best models that are 3 variable, so on and so forth. However, the computer has to do all the math regardless. That just controls the feedback you get. So while best subsets is comprehensive, the more feature variables you have and the more observations you have can do a lot of work. It can take a lot of time on the computer, so just be aware. So this video is about forward selection. Let's focus on that. In forward selection, feature variables are examined one at a time. So we look at all of our variables, find the best one to see if it can go into the model. If it can, we put it in. Then we look at the remaining ones, find the best one, put it in possibly, find the remaining ones, and so on and so forth. You, the analyst, will set a stopping rule. There are several stopping rules. One is p-value, and there are others, but we're going to use p-value for now. It's easier to understand. And it acts as a hurdle, or like a gate, the variable must overcome to be allowed into the model. The added variable must reduce error significantly, and I do mean that statistically, so it must be statistically significant. The feature variable that reduces model error, what we call SSE, the most, is chosen to go into the model so long as it passes the stopping rule. Now, once a variable is in the model, it stays. It is never removed. Then the process repeats until all variables are in the model or no variable passes the stopping rule. So you can kind of see how this works. Now, there are several flaws in forward selection. The ability of variables to reduce error can change, and most likely will change, as other variables enter the model. As feature variables are added, they begin to overlap and interact in how they explain the variance or the reduced error in our dependent variable or target variable. Since a feature variable stays in the model once it enters, forward selection is not flexible. It is possible for a variable that entered early to fail the stopping rule later as other variables are added, but because of the rules of forward selection, it is stuck in the model. Now, for example, let's just use 3 generic variables for now. So variable 1 enters the model first, then variable 2, then variable 3. Let's say, for the sake of argument, that variable 2 and variable 3 combined reduce error in the model better than variable 1 alone. This may lead to variable 1 failing the stopping rule, but it is stuck in the model. So you can see how this inflexibility is a flaw in forward selection. Now, squared semi-partial correlations can tease out these relationships, and we will look at that in this video. It can also miss suppressor and/or complementary relationships, So I don't want to go into detail here. Might do a separate video on these, but in general, a suppressor variable, also called enhancer variables, are kind of strange. They correlate with parts of other variables, but not the target variable. And they eat up or suppress some of the non-relevant error in those variables, making the model stronger. So picture this in your mind. We have two variables and one target variable. So variable 1 correlates with the target variable fairly well. Let's say 0.4. Variable 2 does not correlate with the target variable at all. In variable 1, there is still 0.6 of the variance left unexplained. Now, a suppressor variable, what it does, it correlates with the 0.6 part of the first variable. See how this works? So what it does, it suppresses that non-relevant error, even though it's not correlated with the target variable, and therefore makes the model stronger. It's pretty weird, isn't it? But that actually happens. And forward selection can miss those. There are also complementary variables. These are negatively correlated with each other, but together explain the target variable. It's kind of a trade-off situation. So a common example that's often used in this situation are measures of skill, where the independent variables are speed and accuracy. So most often, when someone does something faster, they become less accurate. So an example I can think of is typing. So if someone begins to type faster and faster and faster, they tend to make more errors and misspell things and hit other keys. There's sort of a sweet spot in there. Or like me, if I'm painting something in my house, I start to paint too fast, I start missing areas, I start spilling paint and throwing paint around and on the floor. So I got to slow down to get the quality better. So complementary variables are things that offset, kind of a trade-off. And forward selection, the way it is constructed, can miss those relationships as well. So step 1, we evaluate single features. This is where we start in forward selection. So we've been using this housing data that I scraped from the web and kind of massaged for these videos. That's actually based on data around my house. So we have 4 variables that go into that model: X1, X2, X3, and X4. So it's a process. We evaluate each one for the way it reduces error. We find the large F value, so the F ratio. We ask ourselves, in our case, because our stopping rule is a p-value of less than 0.05, we say, okay, that's a large F value, but does it meet our stopping rule of 0.05? If yes, we keep it in the model and then look at everything again. We note our SSE, so our sum of squares due to error that we're trying to reduce, remember, our degrees of freedom. So as we add variables to the model, our model degrees of freedom go down by 1, our error degrees of freedom go down by 1, and look at the p-value. Now, I want to point out that this stopping rule, the p-value that we're using, is completely up to the analyst. It's up to you. So if you want to have a very strict model, you can set this p-value very, very low. And that means that the p-value to get into the model has to be very small. Or you can be more liberal with it, set it higher, and that will potentially allow more variables in the model. There is no right or wrong answer to this. It's really up to you, but 0.05 is sort of a happy medium. Here's where we start in our data we've been using. So remember, this data is based on housing prices sort of around where I live, and I scraped it off the web and changed a little bit here and there. There are 4 variables: square footage of the home, whether or not the home is in an exemplary high school district, the number of bathrooms in the home, and the number of bedrooms in the home. So this is where we start. Now at this stage, remember, there are no feature variables in the model at all. If you look at the entered column here, nothing is checked. Now I want to point out a few things to keep in your mind as we go forward so I don't have to repeat them over and over. First thing to point out is that in this case where no variables are in the model, the sum of squares due to error is the same as the total sum of squares because there are no variables in the model yet. They are the same thing. So the SSE of 552777 is our SSE, but it's also our SST at this stage. Degrees of freedom, DFE, that's degrees of freedom for error or due to error, 99. That's our number of observations of 100 minus 1. That's where the 99 comes from. The root mean square error, RMSE, where does that number come from? Well, if we take our SSE, which is our SST, the same thing, of 552777, divide that by 99, our degrees of freedom due to error, we'll get about 5,580, something like that. Take the square root of that number and you will get 74.724 approximately. That's where root mean square error comes from. Now the R square is 0. We don't have any variables in, so we're not explaining away any of the error yet. So we can't have an R square. And the other things we'll worry about later. So here's where we're at. Now this output is from JMP, or JMP, which is from SAS. And it's going to tell us what's going to happen next. And it is giving us what happens for each individual variable. So what it's saying here is, okay, of these 4 variables, which one will eat up or gobble up the most sum of squares in our model? Now, if you look here, square footage is the variable that eats up the most sum of squares. Its F ratio is 152.175, and its probability is very, very small. So, given all 4 of those variables, that's the one we're going to pick to enter the model first in forward selection. So, we go ahead and put that in the model because it has the largest sum of squares and overcomes our stopping rule that we set before. Now let's look at the top line of this output here. Let's look at what changed. So, our SSE, our error, is all the way down to 216,537 approximately. So we reduced that sum of squares by a large amount, the SSE by a large amount. Well, how much? Well, look at the sum of squares in the square foot row. That's 336,240 approximately. Well, if you add that to 216,537, add those two together, you're going to get 552,777. That's the variable we entered first. Now, if we go up here to our DFE, it's now 98 because we added a variable, so we went down one. The RMSE, same process. We have our SSE divided by DFE, take the square root, now we get our root mean square error. Now our R square is the proportion or the percentage of our total sum of squares, 552,777, that is occupied by the square foot variable of 336,240. So 336,240 divided by 552,777 will give us an R square of 0.6083. So that's where those numbers come from. Now we've entered the first variable into the forward selection process. Now we look for the second variable. Again, we look at the other 3 variables and say, which one reduces the sum of squares the most? Look at its F ratio, will be the highest, and look at its probability to see if it meets our stopping rule. Well, in this case, which one is that? Well, it's number of bathrooms. So we select that for the second variable. We put that in, and here's where we are. Now what changed? So look at the top row of our output here. Our SSE is down from 216,537 to 166,099 approximately. Our degrees of freedom due to error is 1 less because we added 1 more variable, it's 97. Root mean square error, so 166,099 divided by 97. Take the square root, and we get 4138 approximately. Our R squared is 0.6995. Well, where does that come from? Now this is tricky because I'm going to trick you here. I want you to see something. You'll see that the sum of squares due to error is 166,099. So keep that number in your head, 166,099. Now, look at the SSE at the top, or the SST, which is the same thing, of 552,777. So the difference between 552,777 at the top, 166,099 at the bottom. Well, the difference between those two should be what we have in our model. But if you look down at the output below, look at the sum of squares for square footage. It's 156,630. Look at the sum of squares for number of bathrooms, 50439 approximately. Well, if we add together those two sum of squares down there and look at the difference between 552,777 and 166,099, those don't add up. It's not enough. There seems to be sum of squares missing. Now remember what I said, that the sum of squares that we see in this output are the sum of squares into the model by each variable on its own. Guess where the missing sum of squares is? It is in the combined explanatory power of square footage and bath. Just with some simple math, we can find where something is missing. It doesn't really add up here, but we know we have 2 variables in the model. We have the sum of squares for them individually. So to get the difference, we have to find out what's missing. And in this case, that is the combined explanatory power of the 2 variables. Now, the numbers up above are the same. So the r squared of 0.6995, that's going to be the total sum of squares explained divided by the 552777. And we can figure out sort of what's missing in there. Same basic process. I want you to understand where all the numbers are coming from, where some of the numbers might not add up if you look at them, so you know what's missing and how to explain everything. All right, so our final step. We have one more variable that qualifies to enter, that is exemplary high school. So we go ahead and enter that there in the blue color. Look at our sum of squares to the error. It's down to 147815, which was like 166 something before. So we reduced more error. Degrees of freedom due to error went down one more to 96. Root mean square error went down again because remember, it's SSE divided by DFE, take the square root, and we have a root mean square error of 39.24 approximately. Now we have our r squared of 0.7326. Now remember, if we add up the sum of squares for all three of these variables we have highlighted here, so 117234, 18284, 46393, if we add those up, that's not enough sum of squares to explain the difference between total sum of squares and SSE up here in the upper left. So where is it missing? It's in the combinations of variables. And we can actually figure that out with some simple math. We'll do that here in a little bit. So that's where everything is. What you're looking at here are the individual contributions of each variable to the sum of squares explained out of the total. We are not looking at the interactions or the combinations of variables. We'll have to figure that out on our own. So we enter exemplary high school. It's the largest sum of squares and overcomes our stopping rule. But we're going to have to reject the beds variable. It does not overcome our stopping rule. You can see that we have a probability of 0.286. That's way above 0.05. So we stop there. That's it. This is our model. Based on our stopping rule, this is our model. Now, if we were very, very sort of liberal in our acceptance of a variable in the model, when we set, say, our probability at 0.3, then beds would be allowed in. But we set it at 0.05 to kind of get a threshold so we don't put variables in our model that can lead to complex models or overfitting. So we stop. Now notice that the F ratio and the sum of squares for square footage keeps going down. Some of that error overlaps with other variables. For square footage, it went from 152.18 down to 91.47, down to 76.14. It kept going down. And that's because the variables started overlapping with each other, and they had common explanatory power in terms of sum of squares. That's why those numbers go down. This is very important. While this does not happen in this example, this is where forward selection can get us into trouble. It is possible that earlier variables stuck in the model violate the stopping rule as new variables are added and sum of squares is reallocated. So in this case, obviously, square footage didn't get to that point, but it is possible for an earlier variable to violate the rejection rule or the stopping rule and be stuck in the model. And that is the fundamental flaw of forward selection. So let's have some fun and go back into the real world just for a couple minutes. So here is our regression equation from the previous slide that we had, our final model. So we have our intercept, then we have our square footage coefficient, our exemplary high school coefficient, and our number of bathrooms coefficient. So what does this mean? Well, remember, everything's in thousands, so we have to multiply everything by 1,000. So our square footage variable means that each square foot of the home has a value of $73.20. That's how we interpret that. What about exemplary high school? Well, that's an indicator variable. It's either 1 or 0. Either the home is in that district, that kind of district, or it's not in that kind of district. If it's a 1, then we get that value. So being in an exemplary school district adds $28,930 to the value of the home. Then bathrooms is similar, but this is an actual number. So each bathroom adds $35,470 to the value of the home. And that's how we interpret our regression equation. Now, of course, remember I said that this data is from an area around my home. So let's look at what my home would be based on this model. My home is about 1,650 square feet. It's just a modest, relatively small home, for the United States at least nowadays. I am in an exemplary public high school district, and I have 2.5 bathrooms because I actually added one while I've had the home. So I put those into our equation, and that generates a price for my home of $174,915. At the time of this video, I bought my home about 5 years ago. So this is a little bit different in terms of date. So 174,915 is what this model predicts. Guess what I bought my home for a few years ago? 172,300. Look how close this is to what I actually paid for my home a few years ago. If I updated the data, it'd probably be a bit closer. And actually homes where I live have gone up in price the past few months dramatically. But in general, this is a very good model based on my own home. And of course, probably the homes around me. So we can see in the real world how to interpret our regression models, how well it fits an actual value of a home given the data. In this case, it's my home. So it's pretty cool. All right, let's get back to some of the conceptual things in this video. So back to the concepts. For a minute, we're going to step away from the house price data and talk about some general information. So let's say we have a variable. We'll call it V1 for variable 1. And it explains 40% of the variance in the model on its own if we just do one variable and the target variable. 40% of the variance. So it'd have an R squared of 0.4. Let's say we run V2 the same way on its own. So V2 and the target variable. And let's say it explains 30% of the variance. So it would have an R squared of 0.3 on its own. And then we have V3, so our third variable, and it explains 20% of the variance on its own. Therefore, under the rules of forward selection, V1 obviously would be entered into the model first, assuming the stopping rule is met. So we have V1 here with 40% of the variance on its own. But let's say V2 and V3 combined explain 45% of the variance. Now, what could potentially happen? Now, it could be the case once we have all three variables in there, the importance of variable 1 decreases dramatically, at least conceptually. So while this is exaggerated for this educational purpose, it is important to know that this kind of thing is possible. So forward selection can leave us with a variable that loses explained variance over time as the model grows and the sum of squares is shifted around based on the relationships between all the independent feature variables and the target variable. So back to our housing data and the allocation of sum of squares. Remember that our total sum of squares was 552,777. And our final model, here at the bottom, our SSR, which is the sum of squares built into the model, is 404,963. Now, how do we figure out that number? Well, we just take 552,777 and subtract this SSE down here of 147,815 approximately. There's a bit of rounding in here, but you kind of understand how that works by this point after studying statistics. So we subtract 552,777 minus 147,814, 815, depending on how we want to round. That's how we get the SSR. So SSR is the amount of sum of squares our model has managed to eat up or vacuum up into the model. And if we take 404,963 divided by 552,777, we will get our R square down below of 0.7326. That's where that number comes from. What is this Venn diagram over here on the right that everyone freaks out? Hate Venn diagrams. Oh my gosh, end of the world. Well, what we've done here is we have allocated the sum of squares to every possible component of our three variables. The first part's kind of easy. Remember the output down here in the SS column tells us the amount of sum of squares in the model that goes just to that variable. So if you look at our Venn diagram here, the square footage variable here in this yellow color, if you look at the 117,234, that's just in the square footage area. There's no overlap there. If we look at our sum of squares down below, 117,234. For bathrooms, it's 46393. Down below here, it's 46393. For exemplary high school, 18284, 18284. How do we figure out the rest of the numbers in this Venn diagram? Well, I'm not going to go through all the math and the puzzle that are Venn diagrams in this video. If you want to see that, I will be happy to make another video about it and walk through the process. But basically, it's a simple Venn diagram puzzle that a lot of us are familiar with. We find out what we know, what we're missing, what we can add and subtract to get the missing parts, and then go from there. So in this case, we know we have the 3 large areas. That way we're missing the overlapping areas. And then just through some math and what we're missing, we can figure out the other areas. And that's what it comes out to. We can see that actually the overlap between square footage and bath without exemplary high school actually has the most sum of squares in it. 125,304. And if we actually added in this area of exemplary high school, it's even more. But the most sum of squares is actually in the area overlapping square footage and number of baths. And that is where we find the missing sum of squares when we add up this SS column down here in the output. It's in all this overlap here. But all these numbers check out. I'm not going to go through it, step by step, but this is all correct. So you can see where everything lines up and overlaps and how the variables interact with each other. Now we can just do some division to find the R squared for each one. All we do is take the numbers in the previous slide and divide that by our total sum of squares of 552,777, and that gives us the R square for each component here in our Venn diagram. So we can actually see the relative importance of every single area and every single overlap of all 3 of our variables in the presence of each other. Now in the output screenshot over here on the left, I've highlighted the R square and the sum of squares for square footage. So how do we match that with what we see over here on the right? Well, remember that what we see down here in the output is the contribution of square footage by itself. So if we add up the sum of squares, 336,239, or 240, if we round up, from the previous slide, let me go back. So if we add up everything in this yellow circle, so 117,234, 125,304, 54307, 39395, add those all up, and we will get sum of squares of 336,240. Now, if we just do the division of the total sum of squares, we divide those by the SST, then we have all of these decimals. Well, look at our R square, 0.6083. Well, guess what? If we add up 0.2121, 0.2267, 0.0982, 0.0713, guess what those 4 add up to? 0.6083. So you see the R squared? The sum of squares divided by the total sum of squares gives us our R squared if we look at square footage on its own. And then the total for all the sum of squares, if we add up everything in the Venn diagram, we can add up the sum of squares and divide by SST, or we can add up these decimals, gives us the same thing, 0.7326, and you can see that in the full model down here below, 0.7326. Now, there is a special name for these decimals. They're called the squared semi-partial correlations, and they are extremely important in understanding the contribution of each individual variable, each combination of 2 variables in this case, and the combination of all 3 variables. So what this is telling us is that square footage just on its own, without either of the other 2 variables, just on its own, explains about 21.2% of the variance in our target variable. This tells us that bathrooms on its own, number of bathrooms on its own, explains about a little over 8% of the variance in our target variable. Exemplary high school, a bit over 3%. Now, the cool thing is in the combination of them. So if we look at square footage in bathrooms without exemplary high school, that explains over 22% of the variance, 0.2267. See how this works? And we can just add these together to figure out which sort of combinations, which area of the sum of squares, which combinations of the R squared actually contribute most to the explanation of the variance in our target variable. It is so cool. So we got all of this just from our generic output here in JMP, but other software programs do the same thing. And we can really begin to understand our model. We can see here that square footage and its combination with number of bathrooms, they overlap quite a bit. So that means there's a lot of relationship between the square footage of the home and the number of bathrooms, which makes sense, right? A bigger home is probably going to have a larger number of bathrooms in it. Well, that makes sense. Look at the R square values here. We can really understand what is going on in our model if we just know what is what, where the numbers are coming from, where they go, and then we can explain that to stakeholders in our model, in our reports, in our business, whatever else it might be, to actually have a good communication to the end user. and of course, build better models. So quickly, for those who are interested in how these come about, so the squared semi-partial correlations is the unique contribution of the IVs to the DV, and there are other ways you can look at them too, but we'll look at them this way. So here's what we have in our output. This is the final model. So the squared semi-partial correlation is this formula. It's actually very simple. It might look crazy, but it's very simple. It's just the F ratio divided by the degrees of freedom for error or residual. RES means residual, error, same thing. So a F divided by degrees of freedom residual multiplied by 1 minus the R square value. For example, to find that number of 0.2121 that we saw in the Venn diagram, we can prove it. The F ratio for square footage is 76.139 divided by 96 degrees of freedom. That's our DFE. Then we multiply that by 1 minus 0.7326. That is our R square up there. Do the math out. We get 0.2121, which is exactly what we had in the previous slide. For number of bathrooms, same thing. Exemplary high school or not, same thing. These are the exact same numbers that we had in the Venn diagram in the prior screen. It is all related. And then lastly, this is where we started. So we had no variables in the model. So you can see the contribution of each individual variable here. If we ran univariate models, so each variable with the target variable on its own, remember we had an R square of 0.6083 for square footage, 0.2099 for exemplary high school, 0.4162 for number of bathrooms. That's on their own if it was a one-to-one relationship with the target variable. Now in the model, we ended here. So square footage was reduced to 0.2121. Exemplary high school was reduced way down to 0.0331. A number of bathrooms way down again to 0.0839. And I put this slide in here to point out to you how the relative importance of individual variables changes, sometimes drastically, when you enter other variables into the model due to the overlapping sum of squares, the correlations between independent variables, and of course the dependent variable. So you cannot really look at a model until you have all the variables in it to know which variable is actually contributing to the variation in the target variable and how they overlap and explain each other. So in this case, square footage on its own, if you're looking at one-to-one, explains the most variance in our target variable. And that's sort of the in-depth look at forward selection. Now, the cool thing is that when you get this final model here, this final output, regardless of which technique you use, these fundamentals all work the same. So we're going to have a list of variables that enter the model. We will have our sum of squares, our F ratio, and everything, regardless if we use forward selection, backward elimination, stepwise, or even best subsets. But now we know how to interpret it. And of course, I will point out while we're here at the end that at the top here, we have no variables in the model, but we have an intercept of 207.3. Remember what that represents. So what that represents in this data set is that the mean house price is $207,300. And that's how we interpret the intercept with no variables in it. Well, that was awesome, wasn't it? You really understand this stuff when you dig in and try to figure out what's going on and how the numbers relate to each other. And then you can understand your model better and understand how it explains, which is your ultimate goal, the target variable. And you can build better models, but also interpret them, and you can explain them, and you can understand them. It's not enough just to run numbers through a computer software. It spits out some table or whatever else, and you're like, well, there's my model. No, that's not enough. So you have to go in and understand actually what's going on and how all the relationships exist between your variables. So I hope you found this helpful in deepening your understanding of multiple regression and building these type of models. And we'll go into the other ones, of course, but once you understand the concepts in this video, it makes understanding everything else after it much easier because the basic concepts are the same. What's different is just the process by which variables enter or leave, or we evaluate models midstream. So once you have this, you got it. So thank you very much for watching. I appreciate you spending your valuable time with me. Look forward to seeing you in the next video. Take care. Bye-bye.